Welcome back, and we are continuing our study of statistical mechanics of ideal gases. Till now we have done monatomic and diatomic, and not only that, we have done the statistical mechanical, we derived the statistical mechanical expressions of free energy, entropy and specific heat. For monatomic we did the translation, that part remains invariant in the diatomic, but diatomic brings the two new ingredients, one is the rotation and vibration, and we have used the harmonic oscillator model of quantum mechanics to derive expression for those quantities for harmonic oscillator, and we showed that this is one of the most respected, used and time honored model applied to many systems of physics and chemistry and biology. And then we did the rotation using the rigid rotator. We worked out again the statistical mechanics. Now, many of the systems that we are interested in, like water, ammonia, alcohols, they are all polyatomic molecules. And polyatomic molecules have characteristics which are quite different from that of diatomic. The reason is that the polyatomic will have now, in addition to translational degrees of freedom, and rotational degrees of freedom, it has vibration, which is many more now. As we all know, that number of vibrational degrees of freedom is more in case of linear, because their rotation is only 2, but for nonlinear molecules where you have 3 rotation, we have 3 and minus 6 the vibrational degrees of freedom, and this is what actually gives rise to when the large molecules like polymers form, or when we form, they are sitting together in a crystalline form, in a solid amorphous, then we lose the translational degrees of freedom that they have, and that get transferred to vibration degrees of freedom, and that shows up as the normal modes, which are play so important role in the specific heat and thermodynamic properties of low temperature solids, not just crystals but also amorphous materials, and these are low temperature liquids, they are very important quantities. So, but however, the polyatomic molecules have many other peculiarities of their own that we are going to discuss today, and they want to do how to do statistical mechanics of polyatomic molecules, so that a student knows how to start talking of entropy and free energy and specific heat, the molecular component of the polyatomic molecule, and that statistical mechanics gives you, and we already have it, but so we will have a slightly more generalized form of what we did in diatomic, and so it will be not too demanding a session. We did do in a small way the polyatomic earlier, but we are going to do a little bit better now, and in certain sense also it is a review of many of the things that we are going to do. Okay, and we wrote down before, we are neglecting the electronic degrees of freedom, because electronic energy level gap is much larger. Typical electronic energy levels are of the order of say 10,000 centimeter inverse, 7,000 centimeter inverse, which are huge. So, they do not enter at the room temperature, the ambient conditions, electronic degrees of freedom, it does not show up in the thermodynamics. It does show up in the spectroscopy when you are giving external source of energy and resonance condition and exciting, but in the thermodynamic properties, it is a ground state of electronic degrees of freedom that is all that you need to worry about, and we can take that energy as a 0. So, that just it does not change with temperature, it does not change with pressure volume, we do not need to talk about it. So, then I can write the partition function as a product of 3, as we already discussed, that it is translation, this is a molecular partition function. So, this is a molecular partition function, and the molecular degrees of freedom, the molecular partition function q, small q is my notation for and capital Q is my notation for the partition function of n particle system. So, then these Q translation, Q rotation and Q vibration. Now, translation is the center of mass, so we do that. Then if you have a nonlinear molecule of 3 rotational degrees of freedom, I call it q dot 1, q dot 2, q dot 3, and then I have all the other degrees of freedom that is given here, and that is of course not just 3, if there are 3 vibrational degrees of freedom, then it is 3, but otherwise that can be many more degrees of freedom that would be showing here. So, and that is shown here. So, since they are all these vibrations are independent of each other, the normal modes, then q vibration is a product of all the vibrational degrees of freedom, which is written here, that I have a nu stands for vibration in the notation and j is the different normal modes. So, then my total vibrational partition function is product of e to the power minus theta nu j by 2t and by t, because remember theta, and this is the alpha is given here, and theta nu j is the vibrational temperature, and this one is the one that comes from 0 point energy, if I to remind you, and this is the one that comes from the detailed sum of this power series, which x 1 plus x square, and that becomes 1 for x less than 1, because 1 over 1 minus x. So, this is the one we derived. It derived in the last or the one before last class. So, now we know this. So, then we can set up the partition function now. So, vibrational part is fairly simple. Vibrational part is fairly simple because we have this thing, and you give me the frequencies and give me that gives me the vibrational temperature, and I can give you the partition function. So, now we will concentrate on the rotational part. Rotational partition function is very important in polyatomic molecules, and because there is a this kind of can be jittery and all the kind of motions that many times you face are basically some kind of restricted rotation. Now, rotation has fairly different cases we need to consider. One case where all the moment of inertia are the same, because there are 3 directions in a nonlinear molecules, and you can have 3 principal axes and you have 3 moment of inertia. Now, if this is completely spherical, we call spherical top molecule like methane, then we have no problem. We have all the moment of inertia are the same, which is like IA, IB equal to IC. The spherical top, the degeneracy of the rotational energy becomes 2j plus 1 square, if they are equal principal moment of inertia, then all this, and we can then write these 2j plus 1 the degeneracy of the rotational energy levels, the equal principal moments of inertia is, then you do, instead of this product we will have 2j plus 1 square, and then we get this expression for the rotational partition function, and then we take the following limit at high temperature. When temperature becomes very high, then and moment of inertia also not too small, then the ones that will be involved are very large j, large quantum numbers will be involved, and large quantum numbers, then I can approximate j plus 1 by j, that is a very neat approximation, and then my rotational partition function becomes this becomes 4j square, this one, then it becomes like, then this is a beautiful thing. So, in the high temperature limit I can do this integration now, it is no longer the difficulty I had, but remember even in the diatomic case we could evaluate the large high temperature limit. Here also then the high temperature in the polyatomic case, the high temperature limit can be worked out, and again we get a very neat expression of the rotational partition function. So, continuing, we now do symmetric molecules. Now, symmetric top molecules are the ones which are like symmetric top, which are 2 moment of inertia are the same and third one is different. it can be prolate. In the prolate, if it is a prolate, then in this B and C are the same moment of inertia and this A is different. So, moment of inertia IA is less than IB equal to IC, that is prolate, and it can be oblate. In the oblate case, then it is these things. So, this direction C is different from in the spherical direction, which is A and B. So, prolate and oblate are two different things, and in that case we can calculate the partition function by using the method similar to this one, that remember that if you go to rotational case, in the diatomic case, the partition function is 8 pi square I by kBt 3 by 2 h square. Then the same thing happens here. So, the quantity is that two of them comes with 8 pi square Ia kBt by h square, half and half. So, when A equal to B, then this half and half becomes just 1, and then you have this C half. Okay. So, whatever I do, either prolate or oblate, depending on A and B, like for example, in the case of prolate, it would be A here and then okay, B here and A here. In the case of oblate, it's the other way around, A here and C here, just the same thing. Of course, the values can be very different. So, but then one comes the most general case with the asymmetric top molecule. In asymmetric top molecule, all the principal moments of inertia, and this is the general case, like the case of water molecules, case of methane, they are all asymmetric top molecules, where all the moment of inertia are different. And this analytical expression of energy levels cannot be obtained by solving Schrodinger equation. That is the real unfortunate part. So, in the previous case part, this case, this thing comes from solving the Schrodinger equation, the degeneracy factor of a spherical top molecules, that it is 2j plus 1 plus whole square. For a polyatomic molecule, this comes from Schrodinger equation. However, this case, in the case of completely asymmetric molecule, we cannot solve the Schrodinger equation, and as a result, we cannot get those energy levels. So, Schrodinger equation cannot be solved analytically. So, for the diatomic we get analytically, for symmetric top, the spherical top, we get it analytically with the different degeneracy. Now, for the prolate and oblate, we again get prolate and oblate when they decompose separately, and we can get the energy levels again, and we can solve for the at least high temperature limit the partition function. But in the case of fully asymmetric molecule, where moment of inertia A, B, C are different, it cannot be, we do not have any closed form analytical expression for the energy levels, and that poses a problem. So, in that case, the Schrodinger equation has to be solved numerically to obtain the energy levels. This is very, very difficult, and this is a laborious process. But we can obtain this classical limit, the high temperature limit, that the high temperature, as I said, the quantum goes over to classical partition function in the high temperature. That means I can start partition function from classical Hamiltonian, I can do from quantum Hamiltonian, then I can show that high temperature the quantum goes over to classical, which is very nice and has to be, because there is nothing, no surprise there at all. But in this case, where you cannot do anything in the for the quantum case, because energy levels are not known, we can do anything other than numerically. That is actually done many cases numerically, one solves and gets the, but we can make progress with the classical Hamiltonian, which can be done, and classical Hamiltonian of course can be just integrated. I write down the moment of inertia, I have A, B, C, and write down there is no potential energy, still it is just the rotating, and it has the rotational kinetic energy. And rotational kinetic energy, I know how to do the rotational kinetic energy, the rotational angular momentum divided by 2I, and then I can integrate that, and that we know that gives this kind of form. So, now I have one for A, one for B, and one for C. So, I have 3 and total rotational partition function is product of these 3, which is just the one we got in classical from classical statistical mechanics, or the high temperature limit of the quantum diatomic case with one moment of inertia. But here also, when they are written in terms of moment of inertia, they are already decomposed. And then we can get that, and then we can write the rotational partition function. I can combine these things and define theta A, theta B, theta C in terms by using all these quantities, because that quantity then becomes 1 over theta B, 1 over theta A, and that becomes 1 over theta B, and this becomes 1 over theta C. Then my partition function becomes this quantity, root over pi by sigma t cube theta. This is a very neat, very nice and neat and very elegant expression. And remember, the half is preserved now, because each comes with a half, and that half shows up here. So this is the rotational partition function, that complete rotational partition function of a polyatomic molecule. So now we have this. So we go back and we have the we go back and we have this total partition function, and now we want to do certain thermodynamics with this expression, and what are the kind of values that you get. Okay. So let us now consider some specific cases. Now the temperature, the rotational temperature and vibrational temperature gives you a measure. This is a very important thing. They give you a measure of the quantumness of the system and the importance of that particular mode in my thermodynamic properties. For example, in case of water, I have 3 vibrations. What are the 3 vibrations? One is symmetric stretching, one is asymmetric stretching, other is bending. The 3 vibrations for water. Now look at them. We already know one is 3650 centimeter inverse symmetric stretching, a little bit higher is asymmetric stretching, that is 3700 centimeter inverse. Bending is nearly half of that, that is 1885 centimeter inverse. It's very nicely placed, those 3, and that plays a very important role in vibrational relaxation. There is some of the outstanding discoveries that made in recent times. Okay. Now if we do that, then look at this in case of water. So this is asymmetric stretching, this is symmetric stretching, this is the bending. All right. Now if it is so, then I can easily see that in thermodynamic properties, if temperature, it will be relevant at 5000 Kelvin. No. So at room temperature I do not need to worry. I do not need to worry at all for water. But look at rotation. Rotational temperature are really very low. The 3 moment of inertia of asymmetric, that water molecules, the 3 axes of rotation, they come. So this temperature, that means they are almost classical, and they influence the statistical, they influence the thermodynamics. So I need to take into rotational degrees of freedom in understanding thermodynamics, and this has a very interesting story. So for some time, quite some time, people are trying to calculate the entropy of water. This is actually big game now of last some 15-20 years. What is the entropy of water? Because the entropy of water, as I said, plays a very important role in many chemical reactions. And I give you an example. When a DNA drug goes into DNA, then of course the drug loses the entropy, but the system gains entropy. The way system gains entropy, the water molecules which were inside, were imbibing, were inside the residing inside the major and minor groups, they are displaced. So when they are in minor group, they didn't have any entropy. There is some extra enthalpy, but they are no entropy. So when they go out, they gain lot of entropy. So we kind of take into account, there are 10 molecules that are getting displaced, the 10 molecules going from minor group of DNA to water. So what is the entropy per water molecule? If I know, then 10 times that is the entropy gain in the process. Okay. And then I can use Sacco-Tetrode equation or something to get the A. But Sacco-Tetrode equation still in a liquid water is not a great approximation, but that they get you started. Very, very interesting. Now, when all these calculations were done initially, people were not getting very good agreement of the entropy of water in the. An entropy of water can be obtained also experimentally in a laborious process by starting from all the way from 0 Kelvin ice, then going into make it melt, going to liquid, then we can calculate, take the latent heat of fusion into, and we know the entropy of water experimentally. That was not working that well. Then we realized that we did not take into account the vibration and rotational entropy contribution. But as I show you, vibration is not important, but rotation important. Translation is of course important. So it turns out the rotational contribution to entropy of water is about 30%. It's a huge contribution that comes from a rotation. It is something like that. 1 in the entropic unit, rotational contribution is about 5 or 5.2, and the translational contribution is 17. So if total entropy is 22, you already had a table saying 17, the translation comes, and then this another 5 comes from, and in order to calculate that entropy, I have to use I use this expression. I use to calculate the rotational partition function. I get the free energy A equal to minus kBT ln Q, and I take the derivative of that and get the entropy. That entropy now is extremely important contribution for water. Rotational entropy contribution at room temperature is 30% of the translation contribution. This is really very important that we missed. Is very recently that we missed this thing. This is just about, I think, 10 years old. Now another system of interest is ammonia. In ammonia has again this ammonia has 4 vibrations: symmetric stretching, anti-symmetric stretching, and bending mode. Now those are vibrational temperature, the theta 5 that we define in terms of the frequency, and that is pretty large. So one is 4800, that's very large, a vibration. This is another vibration. These two are some kind of bending modes. I don't remember fully the modes, but they are certainly not bond stretching modes. But even then, these are pretty high temperature. The room temperature, remember, it will be e to the power minus, the contribution comes as e to the power minus theta by T, that would be theta vibration by T. And since theta vibration is so large temperature at 300 Kelvin, even this guy is e to the power minus 4, and e to the power 4 point something. These are of course much larger. So this contribution is minimum. However, the same e to the power minus theta rotation by T, all in Kelvin, look at that. This theta is small. So all these things play a very, very important role. So all these 3 modes play a very important role in the entropy or the thermodynamic properties of ammonia. Similar things you find in sulfur dioxide, nitrous oxide, methane. Everywhere you see the vibrational temperature is very high. So when it comes e to the power minus theta vibration by T, the vibrational degrees of freedom do not contribute significantly at ambient conditions to the thermodynamic properties. So molecular partition function and molecular thermodynamics, the vibration is a silent thing, we do not see it. We find huge contribution of translation, but then a significant 20 to 30, 35% contribution comes from rotation. So rotational degrees of freedom cannot be ignored in when we are doing, and this is a very, very important thing, because see, most of the books and most of the studies that we hear everywhere, that people are doing as if the world begins and ends with monatomic molecules, maybe a little bit of diatomic, like take the phase transition theories and all the things that we will be doing something. We start with spherical molecules, and we end with spherical molecules, like our studies of glass transition theory theory of liquids that we do. They are all models and things we call Lennard-Jones models and others, but they are all spheres. But this is something. So when we did statistical mechanics in 1970s and 80s, we learned towards the end of 70s and 80s when I was doing PhD and postdoc, we really never bothered about, even if the popular textbooks of statistical mechanics, they don't have much of polyatomic molecules. So our emphasis, and the book that I have written, the statistical mechanics books for chemistry and material science, that's why we have a very big discussion of polyatomic molecules and a lot of emphasis given on polyatomic molecules, because these days we are interested in these kind of systems. Okay. So let us continue then. Then entropy of a polyatomic molecule is just a wonderful thing, as I just discussed to you. So this is the thing, the translational part. So entropy, since partition function is Q translation, Q vibration and Q rotation, and then free energy is minus kBT ln Q. So this they decompose, free energy becomes sum of the free energy and entropy becomes sum of the entropy. This is trivial, but sometimes it is good to spell out the trivial thing, because to help the thinking. That is, then this is our Sackur-Tetrode equation, this is the Sackur-Tetrode equation, and then this is the rotational. Now I have arranged it such that most important thing in translation, which water and ammonia has about 65 to 70% of the total entropy. Then the rotation, which is classical limit, but classical limit works out reasonably well, as I showed you in these things. Fortunately for us, this theta vibration is small. So we are okay, because the room temperature is much larger than this. So we can rely doing classical mechanics. This is a lucky break. In quantum, no way, it is too much, it is too quantum, but this is nearly classical. This is very interesting, how lucky one can get sometime. So like for translation you get away by doing classical mechanics. For rotation, for translation you get away. Rotation you also get away by doing, as I showed you, for many of the molecules. Vibration we are not that lucky, but vibration with a harmonic is a good approximation. So this is translation, this is rotation, and this is vibrational contribution to the total entropy, and as I said, this is actually negligible. So these two does the job perfectly for us. So now I have given you a table. Actually, this I have preempted little bit. I told you I already showed this table 17 and 5, which is I was talking from memory, but there it is, that water molecular weight and every detail is given, and these are the 3 moment of inertia I have given in water. These are the things you do not get in the physics textbooks or even earlier versions of StatMech, but now these are so important in the present day research and present day calculations, that polyatomic study of statistical mechanics of polyatomic molecule is an important thing. That is what I am discussing it, though I discussed it a little bit before, I am discussing it again more detail. And as I tell, there is no damage is done by doing it these beautiful things more than once. Okay. So look at that. In water has this nice thing is the 2 of the moment of inertia are very close to each other, and these are these 2, A and B, 1.09 and 1.91, and this is quite different. Now this is what I was saying, 17.41 is the translational part in the entropy unit in the kb, and this is the one that rotation 5.45. But look at vibration contribution is negligible. When you add up all these things, you get this is the entropy of water. Beautiful, very nice. Now the other thing is ammonia. Ammonia, there are these things that 2 things that nearly degenerate, and then this one is larger moment of inertia. Now a very similar story unfolds for ammonia. Translation and rotation. Now rotational contribution little bit larger, that you could guess, because go back, you could guess that it will be larger, because look at the rotational temperature. Rotational temperature of ammonia is lower than that of the other. So, as soon as rotational temperature becomes lower, its contribution becomes more to the partition function and to free energy and to entropy, and right, that is the one that happens. So, if 5.4, 5.91, this is slightly less, but then at the end of the day we have this value of the entropy. And as I said, it is a very important thing in thermodynamic properties to get the ideal entropy. There are many expressions of entropy, and for example, connection between diffusion entropy. There is a property called Rosenfeld scaling, which needs the ideal entropy, ideal gas entropy, and what uses this value of ideal gas entropy of water molecules to predict the diffusion constant in liquid with certain other terms involving, but this plays a very important role in the properties of liquid. Okay. So this area I summarized it here, that this is straight from the book, Statistical Mechanics book. The StatMech book by CRC Press. From that it is taken that a translational entropy contribution the most, but also rotational contribution is, this is my favorite. I did not know myself about 5-6 years ago. The rotational contribution is 30%, because we also grew up like doing as if everything is Leonard Jones, as if there is everything can be modeled as spheres, but then you miss out all these things. Molecule vibration entropy is only considers intermolecular mode, that are not very important. So, the contribution rise from vibration is negligible. So, this is very encouraged to carry out numerical calculations of polyatomic molecules like chloroform. This is a homework that we will set up to make you do something like methanol, and you can calculate them by doing the homework things. So, here ends the statistical mechanics of ideal gases. I just summarize what you do in 1 minute, that we have done now in great detail monatomic gas, which is spheres, non-interacting spheres. Then with the diatomic like nitrogen, oxygen, they are rotating and they have vibrational degrees of freedom. Vibrational degrees of freedom has beautifully comes with this harmonic oscillator and the Schrodinger's solution. And however, in thermodynamics, those vibrational degrees of freedom do not play a role, but translation rotation plays. Then we went to polyatomic molecules and we did statistical mechanics of polyatomic molecules, the very important case of water, very important case of ammonia and or other sulfur dioxide and all other important molecules that we need to do in everyday life and in real problems, like and that then at the end of this part. So, stop here, we will take a break and we will go over to the next class.